Hello and welcome to this four-part series of lectures about the Doppler applications in medical sonography. We have four parts. Part one is Doppler principles. Part two is talking about the Doppler spectrum waveform. Part three will be about the color and power Dopplers, and part four will be about the Doppler artifacts. My name is Mark Youssef. I'm a DMS instructor. Before starting, I would like to thank all my colleagues for their support, and specifically Mr. Vijay. Also, I'd like to thank my dear students who allowed to be scanned to provide the images used in this series of lectures. So let's start. To start, we need to know something about the word Doppler. Doppler is the name of a person. Name was Christian Doppler. He was an Austrian scientist, and he observed and studied this phenomena. This phenomena is a natural phenomena, so it is not an invention. This phenomena it happens when we have moving objects and waves. Any kind of waves, like sound waves, radar waves, electromagnetic waves, light waves, and any moving object. In our study, that will be the moving blood, but in nature we might have moving stars, we might have airplanes, we might have moving vehicles in the streets. So all of these are the examples of the Doppler principle or the Doppler effect. So in the field of ultrasound, we'll study this Doppler shift. We will study the definition. What are the types of this Doppler shift? It could be a positive shift or a negative shift. What are the factors that are affecting this Doppler shift? And they are collected in what we call the Doppler equation or the Doppler formula. Also, we'll have an overview about how this Doppler shift is being extracted and processed in the ultrasound machine. So, what is the definition of this Doppler shift? Doppler shift is the difference between two frequencies. The frequency that's received, which are coming back from the red blood cells and being received by the transducer, and from the original frequency that's been transmitted originally, and we call this FO. So FR minus FO. So as a result of this, we have a formula here. Doppler shift equals what? Equals FR, the frequency of the received frequencies, minus the FO, or the original frequency, that are the operating frequency of the transducer. So now we'll start to study the types of Doppler shift. And we have three types of Doppler shift. We have the positive shift, we have the negative shift, and the zero shift. What happens in the positive shift? It happens when the source or the receiver are approaching each other. So one of them is moving toward the other. In other words, in the ultrasound, it happens when we have the red blood cells are moving towards the transducer or getting closer. What is the phenomena here? The phenomena that we have the waves here will get compact, will get compressed because the movement of the red blood cells. In other words, the wavelengths of these waves will get shorter and I will get a higher frequency. So the received frequency here will be higher, received frequency FR will be higher than the original frequency or the operating frequency. This is the positive Doppler shift. The second type of Doppler shift is when we have a negative shift. This negative shift happens when we have the source or the receiver are moving away from each other or spacing apart. So what happens in ultrasound? The red blood cells usually they are moving away in a direction away from the transducer, ending by what? Ending by the waves here will get longer wavelengths. So the longer wavelength, I'm getting a lower frequency. So in other words, I will get the frequency or the received frequency will be much lower or lower than the operating frequency. Why? Because the red blood cells are moving away from the transducer. The third type of Doppler shift is a zero shift. Zero shift means what? There is no movement at all. So there is zero, the frequency of the received and the frequency of the operating frequencies are exactly the same. when this happens, when you have the distance between the source and the receiver is constant. For example, I'm scanning soft tissue. Soft tissue, we don't have movement, either the transducer or the tissues. I get here 0 Doppler shift. Another example that when you have the source and the receiver are moving in the same speed, same direction. Same speed, same direction, I will get the distance between these two, the source and the receiver, the distance is fixed. Again, I will get 0 Doppler shift. Actually, this is not a practical thing in our scanning because we can't move the blood and the transducer in the same direction, same speed, so I will get a 0 shift here. So this is not practical in the field of ultrasonography. And the last example, and we have the movement of the red blood cells in a direction that is perpendicular to the sound beam. What happens here? The red blood cells are not neither getting closer or getting away. So what happens here? I will get a 0 shift. There are some notes that we need to know about the Doppler shift. The Doppler shift is a frequency shift. It's a change in the frequency, not change in the amplitude or the strength of the beam. The strength of the waves is described, changed in attenuation. What happened in attenuation? The waves getting weaker. So the reflections are weaker in amplitude. But this is not the case in frequency shift. Frequency shift is a change in the frequency, not change in the amplitude or the strength of the beam. Second thing that we need to mention here is that the transmitted and the received frequencies, they are in the megahertz range. While the frequency shift is in the range of hertz or kilohertz. So transmitted waves and the received waves are all in the megahertz, while the Doppler shift is in the range of hertz or kilohertz. This is actually that it comes to the third point, that Doppler frequency shift is in the audible range. What is the audible range? Is 20 hertz to 20 kilohertz. So it is a by chance found that the Doppler shift with the moving blood, usually in arteries or in veins, okay, the moving blood, it will produce Doppler shift that are falling in the range of the audible range. This is the why sometimes when you activate the Doppler waveform, you will hear the sound. The sound is coming from where? Because the Doppler shift is in the audible range, so we can hear it. So now coming to the study of the factors affecting the Doppler shift. Doppler shift, as we know now, that's created when you have moving objects in the presence of waves. So these moving objects and the waves, they all play together in the formation of this Doppler shift. So these factors are collected here in what is called the Doppler equation. This is the work of Mr. Christian Doppler, who found this, or who, after his study, he found that these players or these variables are forming or sharing in the formation of the Doppler shift. So what are these factors? We have here nominator and denominator. The nominator here we have what? Number 2, which is a fixed number. FO, this is the operating frequency or the frequency of the transducer. V, which is the velocity of the blood. Actually, this is what we're looking for. We are looking for discovering what is this velocity. So this is our question mark. And the last thing here is the cosine angle theta. We know that in each angle has a sine and a cosine. So this is the cosine of this angle. What is this angle theta? Angle theta is the angle between the ultrasound beam and the movement direction of blood. So the blood moving in certain direction and it's making an angle to the sound beam. This angle, we call it angle theta. In the denominator, we have C. C is what? Is the average speed of sound, propagation speed of sound in the soft tissue. This is again a fixed number. So if you look at these factors together, we look at them, okay. Number 2 is fixed, C is fixed, which is 1.54 millimeter per microsecond. So actual players here, or actual variables, will be the frequency of the transducer, the movement of the blood, and the cosine angle theta. So if we study the Doppler equation or the Doppler formula, we will see that there are some variables that are making a direct relation to the Doppler shift. So any change in the denominator here, they will give me a direct effect on the Doppler shift. While in the denominator, it will have a negative or the opposite effect on the Doppler shift. So we have here inversely related. So the numerator is directly related, the denominator is the inversely related. If you look at the numerator here, what are the factors? We have the frequency of the transducer, which is usually is in megahertz. We have the velocity of the blood, which is usually in centimeter per second, and the cosine of the angle theta. And we'll see this in details in a moment later. What are these, the cosine and the angle theta? They mean what? So we knew that we have variables that are directly related to the Doppler shift, which are the numerator. Now we come to the denominator. Denominator here actually is a constant number. So it's not a variable, it's not changing, it's constant, we know this, and it equals the 1.54 millimeter per microsecond. So it's a constant number. But it is part of the formula, and we need to consider this. If you have a question about what are the, if you give you some numbers about for example, the velocity of the blood or the cosine of the angle or whatever, you need to make a calculation. Please put this C, 1.54 millimeter per microsecond. It's a constant number, but it is a player in this equation. So as we know now that we have the denominators are directly related to the Doppler shift. So, excuse me. So we're having here a higher frequency probe or a lower frequency probe. What happens? If I'm having we know that the operating frequency, this one here, is directly related to the Doppler shift. What if I'm having a higher frequency probe? What happens? If I'm having a higher frequency, I will get a higher Doppler shift. I will get more likely to have aliasing. Okay. If I'm having a lower Doppler shift, what happened? Because if I'm having a lower frequency probe, I'll get a lower Doppler shift. I'm getting less likely to have aliasing. So if you have aliasing, one of the things that you might use is to use a lower frequency probe. Lower frequency probe is having less likely to produce aliasing. So let's have an example here about the effect of the operating frequency or the transducer frequency over the Doppler shift. If we have the Doppler exam performed using 3 megahertz and 9 megahertz probes or transducers, what will be the result? The result that the 9 megahertz probe will yield Doppler shift that are triple as large as the 3 megahertz. Okay, what does it mean? It means that this transducer that is using a 9 megahertz waves is having higher chances to produce aliasing more than the transducer of 3 megahertz. The second pair here that is directly related to the Doppler shift is the velocity of blood. As we see here, if I'm having a higher velocity, I will get a higher Doppler shift. So higher velocity, higher Doppler shift. Okay, can I change it? Actually, no. This is actually the velocity of the blood is my question mark. This is the one that I'm doing all the Doppler shift to get this velocity. So as we see here, it is a player, but actually I cannot do anything about it. It's actually, this is my question mark about this velocity, right? So higher velocities, I'll get a higher Doppler shift. So if I'm having extremely high velocity, what happened? I'll get aliasing. Why? Doppler shift will be high. Now, since we talked about the velocity, we need to know something else, which is called the speed. So, what is the speed? Speed is the magnitude or the distance traveled in unit of time. In ultrasound, in Doppler sonography, we use the centimeter per second. So this is the speed. All right. In ultrasound, also Doppler ultrasound, we use the velocity. So what is the difference? Velocity is the speed, but we know the direction. For example, the direction is a positive shift, meaning that it's toward the transducer. So I'm having here a speed and a direction. If we want to know this, like in our life examples, you have a speed limit, but you don't have a velocity limit. Speed limit is you are giving a limit for your speed. You can't violate this, but you are not limited in your direction. You are limited in your speed. So you can go in any direction. So you are using the velocity. So far the speed is within the limit. So there is no limitation of your direction, but there is a limitation of your speed. That's why we have a speed limit. We don't have a velocity limit. Now we come to the one of the other factors that is affecting the Doppler shift, directly related, is the cosine of the angle theta. And as we see here in this diagram, I'm getting here a triangle. If you remember something about the trigonometry, if we have a right angle here, and we have two other angles, they are not right angles. They are less than right angle. So we have one, assuming that we have this angle. Now we study this angle. If I call this angle theta, what happens? Okay, in this triangle we have three sides or three arms, three legs. Okay, one is the facing the right angle, and we call this the hypotenuse. Hypotenuse is the long arm here. And then we have two other sides or two other legs. We have one that's called the adjacent, and the other one is the opposite. So opposite and adjacent to what? To this angle. Okay, so if I'm assuming that I'm setting this angle, angle theta, I'm having one leg or one arm that is the adjacent, and the other one here the hypotenuse. So in this condition or in these circumstances, what is the cosine? The cosine is what? It's the adjacent divided by the hypotenuse. Again, cosine is the adjacent divided by the hypotenuse. Okay, so this is the cosine of angle theta. It's well known that the cosine is the indirectly related or the inversely related to the angle itself. So if I'm having a lower angle, for example, angle 20 or angle 30, for example, I'll get a higher cosine. Higher cosine gives me, as we see here, higher cosine gives me a higher Doppler shift. Higher cosine gives me a higher Doppler shift. Opposite to that, if I'm having a higher angle, close to 80, for example, or 70, what happened? I'll get lower cosine. I'll get lower Doppler shift. What if I'm having higher angle that's closer to be 90 or 90? I'll get the angle is high. The cosine goes down to 0 if I'm having a higher angle 90. So if the angle reaches to 90, I'll get lower cosine down to 0 and we'll get 0 Doppler shift. And we'll see this in a moment now. So we'll continue with the cosine of the angle, and we know that the cosine of the angle theta is straight or directly related to the Doppler shift. So have a higher cosine, higher Doppler shift. So to understand this in a simple way, I designed this diagram. And I have here the transducer, and this black line is the Doppler line or the scan line. Or in other words, this is the sound beam, Doppler sound beam. And the other end here, or these red lines, these are representing the velocity. Somebody will say they are the same. Yes, because as we see, or we know earlier, that velocity is distance in unit of time. So if I'm having the same unit of time, so I will get the same distances here, it means that I'm having the same velocity. So same distance, same velocity. So say same red colors lines, I'm expressing the same velocities. So I'm having the same velocity, but what happened here? They are having different directions or different angles to this sound beam. So if I'm having here perpendicular direction, what happened? The sound beam will detect nothing. It's just a drop. It was 0 here. What if I'm having the sound beam and the direction of the blood is the same? So the sound beam can detect the whole Doppler shift here. Doppler shift will be 100%. Why? Because I'm having 0 angle here. So this is 90-degree angle. I'll get 0 Doppler shift. 0 angle, I'll get 100%, or the Doppler shift will be 1. So in this condition, what will be the effect here, the other three angles? The higher angle, for example, 60, and then medium 45, and then 30. These are just examples I'm using here. Okay, so if I'm having here angle 60 degree, okay, compared to the 0, I'm getting now some Doppler shifts being detected. The lower the angle, I'm getting more Doppler shift detection. The less angle, so I'm getting here less angle, lower angle. What happened? Okay, more of the Doppler shift. So the lower the angles, as we see here, the more, this is the blue parts here with the light blue, these are the more Doppler shift being detected. Okay, so the ultrasound beam can detect how much of the Doppler shift depends on its angle. And this is actually, if you remember about the trigonometry and the cosine, we mentioned it is what? It is the adjacent compared to the hypotenuse. So if this is the hypotenuse here, and this is the adjacent, so I'm having here the percentage of this compared to this. This is how much detected. Okay, if I'm having here lower angle, the adjacent will be bigger. I'm having the same hypotenuse, but the adjacent getting bigger. So I'm getting now more Doppler shift. If I'm having a more lower angle, what happened? The adjacent getting bigger and bigger. So I'm getting now more Doppler shift out from the same hypotenuse. So the adjacent gets bigger. Now if I'm having the zero angle, what happened? The line here will be flat on top of the adjacent. So the adjacent and the hypotenuse will be the same. So what happens here? The Doppler shift, or sorry, the scan line will get the same or the full velocity detection. So based on this diagram, guys, I can tell that when the velocity of the blood, we're having the same velocity here, we mentioned now, okay? So when you have the direction of the blood is 90 degree, like here, I'm getting the cosine of the angle 90, which is 0. So what happened here? If this is 0, I get 0 Doppler shift, right? Now, if I'm having here with the angle 60, how about the cosine? By calculation in the trigonometry, they found that the cosine of the angle 60 is known to be almost 0.5. So 0.5 or almost 50%. So what happens now? The detected Doppler shift detected, listen to this, the detected Doppler shift is 50% of the velocity, right? But now we will provide something to the machine to let the machine recalculate and give us the true velocity, right? So the Doppler shift is 50%, but the velocity displayed is the full velocity. Now, what I'm having here, cosine 45, angle 45. Cosine 45 is known to be almost 0.7, so 70%, as we see here, 70% of the velocity is being used as a Doppler shift here. Now what if I'm having zero angle? Zero angle, parallel, or 180, 0 or 180. What happened? The sound beam can detect the whole Doppler shift out from this velocity range. So as we see here, this is a large diagram. Okay, the more the angle, the less the Doppler shift. The lower the angle, the higher the Doppler shift, right? And as we see here, I want to explain something in short in this diagram here. For example, if I'm having here, let's take the angle 60, which because this is the commonest one we use. If I'm having the angle 60, what happened? The Doppler shift is 50%. So the 50% of this velocity being obtained as a Doppler shift. So is this this 50% will be the display of the velocity in the Doppler spectrum waveform or in the color? No, because actually when you provide this angle, if you provide this angle to the ultrasound system, it will recalculate it and will provide you the correct velocity out from that 50% velocity that's or the 50% Doppler shift. How? Because I provide this angle through the equation, Doppler equation, to the ultrasound system. We'll come to this later on. Before we continue with the journey of the Doppler shift, and it's better to discuss some points here about the difference between the Doppler and the B mode. Doppler application, usually we have the pulse Doppler pulse is made of 6 to 20 cycles. It gives me a longer pulse compared to that for the B mode. And the pulse here, as it's getting a longer pulse, I'm getting a longer SPL, longer pulse duration, and this might deteriorate the axial resolution, which is a factor actually, and this might have some artifacts in scanning with the color Doppler. We will see this later on in the artifacts. Also, the frequency, which is better frequency for the Doppler. Usually a lower frequency is better. Why? It avoids aliasing. Third point about the incident angle, which is better, is 60 degree or less compared to the B mode. B mode usually is 90 degree. The last point to differentiate is the transducer or the operating transducer, which is possible to use for the Doppler. Usually we can use the Doppler application with operating pulse wave or continuous wave transducer. We know that pulse wave transducer it can operate minimum with one crystal, which is alternating between transmitting and receive times. While in the continuous wave, we have minimum 2 crystals, and these 2 crystals, one of them continuously transmitting and the other one is continuously receiving. Now how about the B mode or the grayscale application? Usually the pulse in the grayscale is a smaller pulse. Smaller pulse, how long? Usually it takes 2 to 3 cycles inside. So that 2 to 3 cycles gives me a shorter pulse. Why is better? Because shorter pulse means shorter SPL, shorter pulse duration means I get a better axial resolution of the image. Second point to discuss here is the frequency. Again, better to have a higher frequency. We know why, because I will get a better axial resolution. The same explanation. So better frequency to be a higher frequency. The third point is about the incident angle. What is the best angle in B mode? Usually it is a 90-degree angle because this 90-degree, it assures that the reflections will go straight to the transducer because the reflection will be having a 90-degree angle as well. So they will go straight to the transducer. I will get a better viewing and better visualization of the tissues. This is why sometimes it's better to put the organ of interest. For example, you're scanning the gallbladder or scanning the anything like portal vein or scanning whatever stone in the kidney or whatever. Okay, I'd rather put it in the center of the image. Why? Because it assures that the reflection or most of the reflections will go straight to the transducer. It assures me a better imaging here. So this is the third point. The fourth point will be the transducer or the operating transducer. Grayscale or the B mode imaging usually is using only pulse wave. Why? Because I have to have a listening time. This listening time the machine is using or the system is using to arrange the depths of the reflections. So earlier reflections will be shallower and later reflections will be deeper. So I should have an imaging time or sorry, the receive time to get for the imaging to be arranged in the screen. So far, what we discussed was the creation of the Doppler shift and what are the factors and what is the difference between the Doppler and the B mode. So now we're going to the next step, which is how this Doppler shift is processed or how this Doppler shift is dealt with by the ultrasound system. So we have here, from this point, we'll discuss the next step or what happens next will be in the ultrasound Doppler system. So the first step for this Doppler shift, as is carried by the received frequencies, received by the transducer and then given to the Doppler receiver. In the Doppler receiver, there is a component or part of this or the function which is called the Doppler Demodulator. This Doppler Demodulator is taking care of this. What is this? Is obtaining the Doppler shift or extracting the Doppler shift. How this is done? As we know from the formula that Doppler shift equals what? Equal the frequency received minus the frequency transmitted. Okay, frequency received is known, yes, because this is the one that's given now by the transducer. to the receiver. What is the operating frequency then? Is the frequency that's been emitted or transmitted by the Doppler pulsar. The Doppler pulsar is sending certain frequency to be used. So this frequency that is being transmitted and the frequency being received are both known now to the demodulator, and that's why it's easy to obtain or to extract the Doppler shift. So the next journey for the Doppler shift, it will be delivered to some components in the ultrasound, in the Doppler ultrasound system, and these components are taking care of this Doppler shift and to process into several applications that we have. For example, the Doppler spectrum waveform, the color Doppler flow mapping, and the power Doppler angio or the power Doppler imaging. So for the sake of simplicity, I plotted the following schematic block diagram or model to help following and memorizing the main applications and display of the Doppler shift. Of course, this block diagram can never represent the reality of the complicated electronics in the ultrasound system. So this is the block diagram I suggested and plotted to help us follow and understand and eventually memorize the Doppler applications. It starts in the upper left hand here by the demodulator. The demodulator is doing what? Is subtracting or obtaining the Doppler shift. And then this Doppler shift is delivered to one of these applications here. One of them is the bidirectional, and this part is using a technology called the Phase Quadrature. This technique or this technology is analyzing the Doppler shift, and it can obtain from the Doppler shift mainly is it a positive or a negative Doppler shift, meaning that is it towards or away from the transducer. This information is delivered to the next step, which will be the digital display. This digital display, it could be for the color Doppler. So if you apply color Doppler on the ultrasound system, what happened? The ultrasound system will operate using what we call the autocorrelation. Autocorrelation, this is the technique that's used to operate for the color Doppler. In color Doppler, if you apply it, you get a color map and a color box. The other technology that could be used also is the fast Fourier transform. Fast Fourier transform is another technology, but it gives us a spectral waveform, or the famous one that we use to measure the velocities. And this one here could be applied or could be operated with either a pulse wave Doppler transducer or a continuous wave Doppler transducer. So we have here two applications or two operating transducers using this fast Fourier transform. The other pathway for the Doppler shift obtained by the demodulator is the power Doppler. Power Doppler is using an amplitude display. It's not displaying the Doppler shift frequency shift. It displays the amplitude of this received echoes or the received wave, not the frequency shift. And this one is known by the Doppler power imaging or the Doppler power angiography. So this one is again the second application. And the third application, this is not famous in our ultrasound system, actually is a separate one, and we'll discuss this in the next slide. So the extracted Doppler shift, as we see here, it can go either for the bidirectional Doppler, and this is the one that is using the Phase Quadrature technology, and it can allow the Doppler shift and come from it by the direction. So the direction of the flow is it towards or away. By the analyzing the Doppler shift, is it a positive or a negative? The second thing here we say the non-directional Doppler, and actually this part or this technology is a separate component. It's not in our ultrasound system. It's a separate device. And this device is usually using what you call the non-coherent technology. So the bidirectional is using the Phase Quadrature technology. The non-directional is using the non-coherent technology. This non-coherent technology is famous for to be used in the fetal heart rate devices. So in here we have a little detail about the non-directional or the non-coherent Doppler, non-coherent Doppler technology, or the non-directional or unidirectional. Sometimes it's giving the same name. Okay, this detects and displays the presence of the Doppler shift, not its direction, not its value. How much the velocity, it doesn't tell. Okay, so in this display we have only if there is a presence or absence of Doppler shift. This is called the non-coherent technology. This is used in the fetal heart rate detector. Okay, and also it can be used in, sometimes surgeons are using this. They're putting a device, for example, at the end of the leg, like at the ankle area, if there is some obstruction in the femoral artery or in the popliteal artery. So they want to do what we call revascularization surgery. It's using a bypass or removing the plaque. Okay. Either way, they do what we call revascularization. So before closing the wound, if they hear sound coming out from the device that is wrapped around the patient's ankle, so it means that now the blood vessel is, or the flow is successful, and they get the leg revascularized. Based on what? Based on this non-coherent technology device that is wrapped around the patient leg, so or the ankle area. So this is a device that use also to detect the flow. So there is only flow or there is no flow. So the commonest application after detecting the Doppler is the bidirectional Doppler. This is the one that is used in our devices, our ultrasound systems. And here what we have a component or a technique or a technology called the phase quadrature. Phase quadrature means what? It can give me an idea about the Doppler direction or Doppler shift direction. So is it a positive or a negative shift? Positive shift, it can tell that the flow is toward the transducer. A negative shift tells that the flow is away from the transducer. So this phase quadrature is doing what? It brings me an information about the direction of the flow. So here is the simplified block diagram for this phase quadrature. So this is the Doppler shift is sent to the Doppler shift here is sent to the phase quadrature, and the phase quadrature will send the information. Now it's analyzed and detected either the flow is away or toward the transducer. It's sent to the digital display, and the digital display is taking this information and send them either to the autocorrelation if you want to get a color flow, or send it to the fast Fourier transform if you want to have a spectral waveform. Of course, we can operate both. We can operate the autocorrelation and the fast Fourier transform if we apply the color and the pulse wave. So in collection, guys, we have here a list of the Doppler application, and most of these are digital. The audio, the Doppler spectrum waveform, color flow display, and power angio, all of these are digital displays. Just a quick hint here about the audio. Audio is not a separate application. It comes together with the spectral waveform. So the Doppler spectral waveform that's using the fast Fourier transform technology is also displaying with it the audio display. Audio display, it comes with the speakers. We have right and left speakers. Usually the right speaker is operating with the towards the flow toward the transducer, which is a positive shift, and the left display, it operates with the flow away from the transducer. So this is the end of part 1A, and see you in part 1B.